Hello everyone, my name is Mohammad Azmal. I'm the founding engineer of iMesh. Since past few years, I've worked on various cloud native applications, ranging from high performance backends to blockchains to full stack apps. With iMesh, I help enterprise adopt Istio into their large scale production workloads. I'm very thankful to Conf42 for having me here. And today I'll be discussing on Ambient Mesh, which I think is the new sidecarless and faster Istio for Zero Trust. A bit about iMesh, we formed in 2023. We offer enterprise-grade Istio support, and we also offer a dashboard called iMesh Dashboard, which you can use to monitor your Istio workload with a mission to simplify and secure your microservices in the cloud. In today's session, we'll be having a look at understanding what is Istio Service Mesh, what are the limitations of the existing service mesh, and we'll be understanding what Istio Ambient Mesh is all about, what are the security and other benefit that it comes with. We'll be having a demo as well where we'll be using Istio Ambient Mesh with MTLS. We'll be applying L4 and L7 authorization policies, do traffic management, and do observability with open source tool that come with Istio, and a lot more. So we have quite a lot of meshes to cover, and I'm sure it's a tongue twister for you as well. So buckle up, and here we go. So in Istio documentation, you can find that a service mesh is a dedicated infrastructure layer that helps you add capabilities like observability, traffic management, and security without adding them to your code. So for someone who is not aware of service mesh, it's basically a layer. It's kind of like a pluggable layer which you add while you're deploying your workload so that you get observability, traffic management, and security out of the box. Let's have a look at Istio service mesh architecture, the one with the sidecars. So as you can see, there are two major components to it, one being the control plane, another being the data plane. So the control plane, which is essentially Istio-D, is responsible for injecting sidecars to all the workloads when a namespace is enabled for Istio injection. So if the namespace is enabled for Istio injection, all the pods are going to be deployed along with a sidecar, which is nothing but Envoy proxy. And this Envoy proxy is the central point where you do traffic management, observability, and MTLS, all those things that Istio provides. Now, once a sidecar is deployed to a particular service, it internally intercepts the traffic. Whatever is going to the service is now going through the Envoy proxy and then to the service. So this is the traditional Istio service mesh architecture. Istio also provides ingress and egress gateways, which are Envoy proxies themselves. But later on that, once we go to the demo. There are various limitations to the sidecar approach, the most pertinent one being the sidecar itself. Since each of your workload needs to be injected with the sidecar, it results in modification of the pod spec and it redirects the traffic within the pod. Also, if you have a massive workload like 4,000 or 5,000 pods or even more, even the lightweight sidecar, when it is deployed on such a massive workload, causes a massive resource utilization. The traffic capture, HTTP processing, which are very computationally expensive, are done all at the sidecar level. It manages L4 routing, L7 routing, L7 observability, L4 observability. There's quite a lot of going on. And if you have to update the sidecar, then good luck. You have to restart the entire application. There is no midway approach that you can you can update half of the sidecar and leave the rest running in an older version. The service first protocol is also a massive issue with the current service mesh architecture with the sidecar, as it impacts the permissive MTLS and it's very tough to work with. And it doesn't even work properly for non-conformant HTTP implementations. How about we break it down? Instead of one sidecar dealing with L4 and L7 and doing everything in between, we separate the concerns using two different layers. One for the L4 secure overlay, another for the L7 processing layer. The MTLS tunneling, simple authorization, TCP metric logging, and routing, all of them can be taken care at the L4 level. Whereas in the L7 layer, you have rich authorization policies, metrics, logging, routing, and everything that you need. The ambient mesh does exactly the same thing. It takes care of L4 and L7 responsibilities differently. There are two components to it. One is the ztunnel, another is the waypoint proxy. Ztunnel, short for Zero Trust Tunnel, helps you to securely connect and authenticate your workloads in the mesh. It is extremely lightweight as it does not do anything related to L7 processing. All it does is provide MTLS and L4 authorization. The waypoint proxy, however, is the one providing you with L7 capabilities. And it is not mandatory to deploy waypoint proxy. You can deploy it on basis of a namespace or maybe even service account, depending on your L7 use cases. So ztunnel, if it sees that there is a waypoint proxy, will pass all its traffic through it so that the L7 policies are being evaluated there. And it again goes back through the other ztunnel to the respective workload. And you can see that waypoint proxies are nothing but envoy proxies themselves. And ztunnel is a different application which is written in Rust, making it very performant. Waypoint proxies are like simple Kubernetes pods which are deployed in a particular namespace. So if your traffic is higher, you can easily scale them up or down, which is pretty easy. Now let's understand what is HTTPS connect tunnel. A ztunnel uses this to communicate with other ztunnel and waypoint proxies as well. It uses HBone, the HTTP based overlay network environment, to encapsulate all the traffic that is coming through the ztunnel into a single port, which is exported as, in this case, that is port 15008. You can see the ztunnel might be listening at port 80, 443 and other particular ports from a particular workload. But at the end of the day, it's kind of encapsulating everything in the HBone and exported through one single port. As a result, the ztunnel doesn't has to manage a lot of connections with the other ztunnel or waypoint proxy, making it very simple as there is only one port which is exported, and the entire traffic is kind of going in this kind of packet, as you can see below. So this clear encapsulation provides better interoperability with load balancer infrastructure. It also works well with the existing Envoy sidecar, the Istio sidecar mesh. And as a result, we also have a better support for server first protocols for your MySQL and other databases where the server kind of makes the first connection. Now let's understand how secure ztunnel actually is. For those of you who know SPIFFE, the secure production identity framework for everyone, it's similar to the workload attestation process. So here you can see the sleep pod is trying to interact with the echo server on a different node, and everything is going through ztunnel and then a waypoint proxy, and the communication is happening. So in between we have SVID, which is SPIFFE verifiable identity, to verify a particular service. Here, since the SPIFFE says, the SVID says that it's from NS, NS1, SA sleep, we know that it's coming from the sleep service. And then it has to go to the echo service, and this is how the ztunnel knows from where to route the traffic. So what's happening is, for generating the certificates for a particular service or particular workload, so Istio D is the one that acts as the root CA. You can configure it to use a different root CA, but Istio D in this case acts as the certificate authority. ztunnel here assumes the identity of a workload which is running on a particular its node, and it acts as a node agent in terms of SPIFFE. It then sends a CSR request to the Istio control plane on behalf of this particular service to get its identity back. Istio control plane then signs it and returns the X509 certificate to the ztunnel. Here Istio control plane is kind of acting like this SPIFFE server which signs the certificates for a particular workload. And this is how the entire certificates are being managed in the service mesh. Now let's have a look at ztunnel in action. This is not the actual demo. We'll be having a demo further in this session. This is just to see ztunnel in action. And as shown in example, here we have a sleep pod, which is trying to talk to an echo server in a different node. This is a local kind cluster, and I'm using two nodes here, which I'll simply use TCP dump and listen for port 80 and the port 1508, which is the HBone port. And the same thing here as well. I'll be doing that. And if I run this, I get the response, and also here you can see the traffic is not encrypted. We can see the request body and the entire response here. So okay, just adding spaces below. Now let's install Istio and enable the namespaces to use the Istio ambient mesh. So is istio-ctl install set profile ambient. We'll be having a look at all the configurations and all ahead in the session. This is just to show ztunnel in action. Let's give it some time to install everything. And once it is done, we just need to label the namespaces with istio.io/data plane mode equal ambient, so that the ambient mesh, the namespaces are kind of in the mesh. Okay. Now I'm running the same thing. We are getting the response back, but if you see here, the entire traffic is encrypted. You're not seeing anything that we saw previously. And these are these are kind of the logs for these different ztunnels and all communicating, but every traffic here is encrypted, right? So yeah, this you can see the ztunnel in action and how it does MTLS. It's just pretty easy. It works out of the box. Now, what could be a better time than this to discuss the benefits of Ambient Mesh? We just saw ztunnel in action, and this is as easy as it can be. So the first benefit is that it can be used without modifying an existing workload. It is a non-invasive method of using the service mesh. You don't have to modify pod spec or do any internal traffic rerouting in a pod. I just label the namespace, everything was working. And once we go to the demo, we'll be able to see it even further in action. There is zero downtime. You don't have to wait for any sidecar to be injected and running so that you can say that, hey, my service mesh is up and running. It is very minimal in terms of cost because you're not deploying sidecars for every particular workload. So that makes it really cheap, both from the cost perspective and the resource utilization perspective. It is interoperable with all the sidecar-based Istio, even non-Istio workloads. So yeah, this is kind of like the best solution of Istio you could ever imagine. Okay, without any delay, I'll be jumping straight to the demo. Since after seeing ztunnel in action, I'm sure you might be wanting the whole picture. So let's hope everything goes well. So this is my cluster setup for the demo. I'm using AKS cluster with 2 nodes. And this is the node specification, as you can see. And I'll be using the Istio version of 1.18.3. So the way this demo will progress is that we'll be starting with this particular architecture and we'll kind of keep adding bits and pieces to it. And as you can see, there is just one namespace in node 1 and another namespace in node 2. Each namespace is going to have sleep and not sleep pods. However, the echo server in NS1 is just one deployment, and in NS2 it has 2 versions, V1 and V2, for us to understand traffic management as well. Now we'll quickly go over the configuration for these deployments. So here you can see we have 2 files, resources NS1 and resources NS2, responsible for kind of deploying various workloads in different namespaces. So I am defining the namespace here, and I'm also labeling it with istio.io data plane mode ambient. So it is taken into the ambient mesh when you install it. So right now we won't be having any Istio. So whatever you install here, it's simply going to kind of be there. And then I have service account for echo service, and I'm using service account for the waypoint proxies. That's why I'm creating it. There is an echo service and then the deployment. Same thing with the sleep server and not sleep. There is a service account, a service, and a deployment. The only thing different in resources NS2 is the namespace, and the echo server deployment is having both V1 and V2 here. Right? So now we'll quickly install the workloads. So all we have to do is apply those 2 files, NS1, resources NS1. Here it's creating the namespace, services, deploying everything. So wait for some time, and we'll also deploy NS2. And done. Awesome. So let's see what we have in NS1. Okay, we have our echo server, we have a not sleep and sleep pods, the services, the deployments, everything is up and running. Let's go to NS2, and we do have 2 echo server here, one for V1, another for V2. So everything up and running here as well. Let's have a look at the pods and see if they are deployed in the right nodes. Yeah. So yeah, the namespace 2 is running on this particular node, 001, and NS1, all the workloads would be running in the node 000. Now moving to step 2, what we'll be doing is we'll be installing Istio. And in this case, I'll be installing Istio with the ingress gateways as well. In the trailer, you had seen just the ambient mesh Istio, but here we'll be needing the Istio ingress gateways. So yeah, let's just copy the command from here. Oops. Okay, istio.ctl, this much. Yeah, I'm lazy. I'm just copy pasting commands. Oh, my bad. What did I do? Command not found. Yikes. Looks like demo gods are not with me. Okay, let's give it some time. It's going to take some time to install. Okay. Istio core has installed. We have the Istio D here. The CNIs, ingress gateways, everything is going to get installed. We'll be having a look at the Istio namespace as well. to see what all things it has. So once it's done for injection, okay, cool. Get ns, we'll be having an Istio system namespace, which is by default. And let's see, kubectl get all Istio system. Okay, maybe I need to reduce the size a bit. Yeah. So here you can see we have the Istio CNIs that are running on different one for each node. We have the ingress gateway, we have the control plane, and we have a ztunnel, which is running on both the nodes. We have the ingress gateway as well. And if we have a look at the pods, you can see the one ztunnel is running in this particular node, another ztunnel is running in this node. So we have installed Istio successfully. And well, after that, we'll also be installing the gateway APIs. We'll be needing this ahead in the demo. Since I've already installed that in my cluster, I won't be running it. You can simply use this command to install it. This is just to install the Kubernetes gateway APIs. Now, since we have installed Istio, let's install Prometheus, Grafana, and Kiali, all the observability tools here as well. So I don't have the YAML files here. I have it in a different location. So I'll simply be going there. Open source Istio 18.3. And then we can simply copy paste the command. However, I don't recommend copy pasting it from PDF. Anyways, you'll be having everything in GitHub. I'll make sure I'll add a proper README to it as well, so you can use it properly. Okay, Prometheus is installed. Let's install Kiali and Grafana as well. Awesome. With this, we have installed Istio Ambient Mesh and all the related add-ons to it. Now let's go ahead. Now in the next step, we'll be labeling our namespace so that it is Ambient Mesh enabled, which I've already done in my configuration. So if you haven't done it, or maybe you're using a different namespace which was pre-created, you can simply label it like this. Now let's test it with the kubectl exec command and see if it's working or not. Okay. And while we are here, we might also need to exec into the ztunnels as well. So I'll be doing that. Before that, let me paste this command and format it so it works. Okay. Let's log the ztunnels. kubectl logs -n istio system. Okay. You can see it's kind of having all the XDS and all service discovery and all is going on. Okay, what was the other pod? Cool. So we have the ztunnel logs printed here. Now let's run this command. Okay. Nice. We are having a response back. It's coming from V2. And yeah, in this case, it might come from V2, V1. We are not doing any load balancing stuff yet. So let it come from wherever it is coming. Yeah, now we are having it from V1. And you can see it's logging all the inbound and outbound proxies. This you can see is basically the kind of IP of this particular services, these ztunnel services. And we have the logs here as well that it is having an inbound connection. We have a resvid printed here as well, so we know from where the traffic is coming. So yeah, this you can see the ztunnel is actually working pretty fine here. And maybe if I do a get svc -n istio system. Okay, let's see what we have next. We have already enabled Ambient Mesh, and next we'll be having a look at the authorization policies. So we'll be doing two things here. One is that first, by default, we'll block all the requests. And in the next, what we'll be doing, we'll be specifically allowing NS1, sleep NS1 to talk to echo NS2. Okay. Now let's have a look at the configurations at first. So this is the deny all L4. Basically, if you create an authorization policy, here I'm just giving the name of the authorization policy and which namespace it belongs to. So then you can see that if you don't provide any specifications to it, by default, if you simply create an authorization policy, it's going to deny everything. So let's see that in action. I'm going here, kubectl apply -f deny all L4, and it has created the authorization policies. And yeah, let's see if that works. Yeah, copied the command here. So here we're trying to talk to from sleep ns1 to echo server ns2, and we'll be getting a command terminated with exit code 56. So this is the policy is basically blocking us to do that. Even in the same namespace, if I just want to talk to echo server 1, right, it's still going to block it. It won't allow anything. Any communication it won't allow. Right. So now let's have a look at how to enable communications for ns2, echo server in ns2. This is the configuration to it. Sorry, this one. So again, similar to the deny all one, we are creating an authorization policy and we are naming it as allow inbound to echo ns2. You can name it anything you want. And the namespace as well we are giving here. And in the specification, we are simply giving the match label for the app, which is echo server ns2, and we are giving the rule. So this action could be either you can allow it, you can deny, it depends. All of these you can see in the Istio documentation regarding the authorization policies. It's pretty clear there. And so here you can see from I'm just giving a source, and in source I have to list the principal. So here I'm listing that, okay, you allow only the request that is coming from sleep account ns1. This is very similar to the SVID you are seeing. It's saying that in local cluster from ns1, just allow sleep service 1 to kind of send request to this guy. Anything else would be blocked. So let's apply this policy. kubectl apply -f allow communications from echo ns2.yaml. Once it is applied, now if we go back and we try to communicate from ns1 sleep to echo server in ns2, this should work and this should give us the response back, and we have it. And now if I try to do the same thing with not sleep, which is in ns1, it would give an error to me. And even if I tried to do it with sleep, which is in the same namespace as that of echo server, that is ns2, it won't work, right? So different exit code it is giving. You can refer the documentation for this. But yeah, on the whole, the L4 authorization policies are working great here. So as we can see, it is blocking the traffic and it is doing all the things. So yeah. Now next we have got allowing traffic through the ingress gateway. So this is, we have seen that we are communicating through the you can say we are kind of exec into the sleep pod, and then we were just writing curl command to communicate. Now what we'll do next is we'll allow ingress gateway, which is the Istio ingress gateway, to communicate with echo ns1, okay, the echo server in namespace 1. For this we need to apply the Istio gateway YAML file, which is the standard Istio gateway. If I simply go there, and you can see in the configuration, yeah, I'll just increase the font size a bit. You can see we are creating a gateway. It's again, it's just the Kubernetes gateway type. The only selector is this Istio ingress gateway. Okay. And then we are saying that for port 80, just allow from all the hosts. So this is very pretty standard gateway configuration. Same thing with the virtual service, the Istio virtual service that we have seen up until now with the sidecar ones as well. Is just giving a name for a particular namespace. I'm specifying that use this particular gateway, which is gateway ns1 that I've made here. And all you have to do is route all the traffics to the ns1 service. Okay. I need to apply this file. So if I go here and I do kubectl apply -f istio gateway.yaml, it's going to apply everything. And you can also do it, you can just get the gateway, right? We have applied gateway ns1 and also the virtual service. It's associated with this particular gateway. And this is the external IP for the ingress gateway. Now let's copy and go over to Google Chrome and see. So right now you'll be seeing that the connection error is happening because remember we applied deny all. So yeah, it still won't allow the traffic until you enable it externally. So there's another file which is simply saying similar to what we saw for the echo ns2. that allow all the inbound traffic that is coming from the Istio ingress gateway. Now, Istio ingress gateway itself has a service account, and this is just what we are referring to right now. Let me apply this file -f allow communication to echo ns1. And once the authorization policy is applied, simply go ahead and refresh it, and now you can see I'm getting everything. You can also see I'm getting the Envoy headers here. So yeah, nice. We have an external gateway, Istio ingress gateway, and that is working well with the Ambient Mesh workloads. So moving ahead, we'll be having a look at the L7 authorization policies. We'll see how to generate the waypoint proxies, how do you apply waypoint proxies, and so what we'll be doing is we'll be restricting the NS1, sleep NS1 to echo NS2 communication to only GET request. We won't allow any post or delete or any such requests. So let's first generate the waypoint, and before going there, you can also get the authorization policies, whatever you applied using the get authorization policy command in kubectl. In this case, in NS1, I think only 2 were applied, one for the inbound from the Istio ingress and another was the denial. Now let's have a look at how to generate the waypoint proxy. You can use the istioctl command. X stands for experimental, waypoint generate, -n ns2 and -s, which is not the service but the service account, which in this case was echo server service account ns2. Let me quickly verify it if that's the case. Yeah, echo service account. Okay, not the server. Nice. Okay, so this as you can see, it has generated the standard Kubernetes gateway API YAML. You can see the kind is gateway. The only difference is that you have an annotation which specifies that this is for which service account. In this case, it is for echo service account ns2, and we have the name here as well. It's just taking the same service account name and putting it as a name, and namespace is ns2. We have in specification, we are specifying that the gateway class is Istio waypoint and just a listener for the hbone. Okay. So what I've done is you can actually you can directly apply it from here as well. Instead of generate, if you hit apply, it would still work. But so what I've done is I've copied this over to a file and I've just changed the gateway name. So it won't be confusing because we already have the names similar to what we had in the service account name. So let's apply this file instead. Again, it's a standard YAML file. You can apply it, doesn't matter. Waypoint proxy.yaml, enter. Nice, we have created the gateway. Okay, now let's have a look. kubectl get gateway -n ns2. See, we have an echo service sent to gateway. The class is Istio proxy. It has its own address as well, which you can see Istio, the gateway name and the Istio waypoint proxy. But let's also get the pod in ns2. Now you can see there is a service, the waypoint proxy pod here as well, which is running. So as we had seen, that waypoint is just a pod. It's nothing different. It's just a pod that is running. You can scale it as and when you like. Let's just log it and see what is happening there. Right, pretty standard Envoy proxy logs. Here you can see nothing fancy here. Anyways, so we have deployed that. Now let's again try to query the ns2. Echo service is ns2 with service 1. So right now I haven't applied any L7 policies yet. We simply have the waypoint proxy and we are just doing the curl command. Now just see what happens if I run it. So previously we had already applied the L4 authorization policies to deny all, and then we allowed the communication. But since I have applied the waypoint proxy as well, I am getting an RBAC error here. Okay, saying that access is denied. Because right now we have the waypoint proxy, but we are again not allowing what things we need to do. So the default is basically it's getting access denied in this case. So in order for us to allow the get request, we can make another policy, authorization policy. In this case, it is going to be an authorization policy for L7. As you can see, I am having a gateway name associated with it, and in this case, I'm using the same gateway name which we had used in the case of waypoint proxy. So this authorization policy would be applied for that gateway. We are allowing the request, and the rule is simple. Whatever was previously there from the source and the principal is basically this. And 2 here stands for what kind of operations are we going to do. You can again refer to the documentation for further kind of in-depth guide as to what these configuration would do. And in this case, we are simply using operations and saying that, okay, allow method get. We are not using anything else. We are allowing that from this particular cluster to echo server, just allow methods that is get request. Okay, let's apply this file. kubectl apply -f allow get request to echo ns2. Okay, now it is created. Now if I try to do the same thing, I'm getting a successful response. Let's try it with post request, and we are getting an access denied. Cool. So this is working. This is the L7 network policies in action, as you can see. So this was a very basic example of how we would apply the L7 authorization policies. So similar to what we have seen in L4 authorization policies, if you don't provide a spec selector, by default it will block everything. We have already seen that since we had not applied anything. And in this case also, if you don't apply anything in operations, the 2 is basically specifying what all operations you want. So if I simply comment this out and I don't apply, it will allow everything. That in this case we are restricting only to get. It will allow get, post, put, and all those things in context of this example. But since we are restricting to the set of operations as methods get only, it will only apply the get request to it will only apply the get request to pass through. Now next we'll be having a look at traffic management. So we'll be doing canary release here. We have already seen from sleep ns1 we are able to query echo ns2 with the get request. Now we want that, okay, the 90% of traffic should be ending up at v1 and the 10% at v2. So to do this, we'll be applying a canary.yaml file. So as you can see, this is pretty standard. You can see whatever you would do in Istio with sidecars, a virtual service that is applied on a particular host. In this case, this is the host of echo server, which is in ns2. And in route destination, we are only saying that, okay, for subset v1, make 90% of the request approximately go to subset v1 for this particular host. And in the other one, we are saying that, okay, for 10% of the time, take it to subset v2. Now the definition of these subsets are there in the destination rule that we have set here. The destination rule is again applied on ns2, and it is selecting echo server service ns2. I haven't applied a full qualified domain name here because it's in the same namespace. So I'm just showing this example that, yeah, it would still work without the FQDN. Okay. So in subset v1, we are simply selecting echo server app ns2 and the version of the app, which is v1. And in v2, we are simply selecting echo server app, that is ns2, and the version, which is v2. Pretty standard. This basically, if you apply this to the sidecar enabled service mesh, it would still work. Nothing different. So now we are going to do kubectl apply -f canary.yaml. Okay, let's wait. Nice. Let's see kubectl get destination rule in ns2. We have the echo service one and also the virtual service. Awesome. Now let's test it. So what we'll be doing is, so we'll run a command which will send 100 requests from the sleep of ns1 to the echo server of ns2. Okay. If I can, I can properly format it, we should be good to go. Yeah, let's run it. It's going to take some time because it's going to fire 100 kind of requests to this particular service. And as you can see, for version 1, I'm just doing a grep to get whatever version it is there in the logs. We can see that 91 of them have this echo server deployment ns2 version 1. And if I simply change it to version 2, we'll approximately get 10 requests in this case. Okay, it's 16. That's still fine. Again, it's not going to be a perfect division of percentage. It will try to approximate it as much as it can. So we are seeing here different number, and you can see the variation is quite huge. So, okay. Now let's see what exactly was it sending here. If I simply do the standard curl command instead of any grep or anything. So let's see what we are actually picking. Oops. Yeah. Right. So we already have a host name that was being printed, and for different pod it's going to be different. So this is what it was, the grep was doing, and we are simply counting the occurrences. So in this case it is again version 1. Let's run it again. Right. It's version 1 again. Version 1. Right. Since 90% of request is going to version 1, we are most likely to get this. So as you can see, canary releases is working well. You can play around, do whatever kind of 50-50. You can do a blue-green or whatever things you could do with Istio. You can do the same thing with Istio Ambient Mesh, and it's nothing offshot, and it's pretty performant as we can see right now. So after traffic management, let's have a look at the observability and debugging capabilities of Istio. Similar to that, what we are seeing in sidecar, we'll get the same things here as well. So I'll be using, let's go to Prometheus first, istioctl dashboard Prometheus. So you can see I'm having all the Istio related matrix, request total. Yeah, I'm getting everything. You can see from destination service, gateways. This is, by the way, the ingress ones. Here also you can see the app was Istio ingress. You won't see a lot whatever we have done from the curl to the NS1, which we had tested previously before applying the deny all, because those are some of the TCP metrics. The L7 ones would come from Envoy itself. So in this case, ingress gateway is Envoy, so that's why we are having L7 capabilities. And the waypoint proxy itself is an Envoy proxy. That's why we are having all the L7 metrics from there as well. However, all the L4 metrics were there. Once you apply the ztunnel, you will be getting all the TCP connection opened, lost, total, all those counts, everything would be there. So the matrix, as you can see in Prometheus, it's working great. Let's have a look at Kiali as well. Yeah. Now if I go to graph and I'm choosing last 1 hour, maybe. Okay, I'll first. Okay. So now you can see in sleep NS1 to echo service, we are already seeing the traffic flowing to version 1 and version 2. The green ones are the previous ones, which we had deployed before the service mesh was there. So this is just the general ones, whatever that has been captured. Now once the service mesh is here, you can see that in the, if I go to app graph itself, you can see everything is in blue, is kind of TCP encrypted. Okay. Where is this version app graph? Right. We had some of the failures as well, which is being captured here. So yeah, pretty much everything is working in the observability section. Let's have a look at Grafana as well. So, okay. I'm going to the available dashboard. You can, however, choose to create your own dashboard. So go to the control plane dashboard and see what kind of metrics we are getting. Nice. So we have a CPU usage, and we have our endpoint, listener, pilots, everything. Whatever we had seen in the Istio sidecar version, we are getting everything here. And let's go to some other dashboard, maybe the mesh. Okay, what's there in the mesh one? Yeah, some of the information related to mesh, how many authorization policies we have applied, what interval, and all those things. So yeah, we also have the service, workload, request, and all those things, whatever was captured here. So you can also do pretty much everything what you were doing with Istio related to observability here. So yeah, that pretty much sums it all. So apart from observability, we can also use istioctl to debug our proxies. So let's have a look at that. So you can use Istio CTL proxy status to get the status of all the proxies deployed. So in this case, you can see especially the Envoy proxies, in this case, which is the waypoint and the ingress gateway. They all have the endpoint discovery service and ECDS and all those things. They are synced, and all the informations that you can see you're getting. The ztunnel, however, is not an Envoy proxy, so all of these things are ignored. You can also use istio-ctl proxy config to have a deeper understanding of the configuration of these particular Envoy proxies. If you just go to the help section, you'll have a list of all the available commands that are there, and you can use it to debug your proxies. So let's try something like proxy get all. So we'll be retrieving all the configuration for this specific Envoy proxy. In this case, we'll be using the echo service one. Yeah. And make sure that once you're giving the name of the pod, you also give the namespace after the dot. So this is how it works. So let's see what we are getting. So we can see that we are getting entire overview of all the full qualified domain name services it has, what port they listened on, or what is the direction of the traffic, also what virtual services you are using for this particular inbound. So this is a pretty handy tool for you to debug, and it also gives information about the root CA as well, as you can see here. So you can also play around with this, and Istio-ctl is a very powerful tool for you to debug as well. So that's all for the observability and debugging. Okay, so if you have been this far, then good job. So we have successfully added Ambient Mesh to our cluster. And if you have any questions related to it, feel free to reach out to me on LinkedIn, or maybe even just create an issue in the GitHub repository that I had shared. So thank you, everyone. Once again, thank you to Conf42 for having me. This is MD Azmal signing off.